Okay, so um, today, as with the last few lectures that I've uploaded, it's going to be most helpful if you have a look with me while I'm doing this at the textbook because, or the online notes rather, because a lot of this involves pictures or quantities that would take me forever to write out, and so it's way easier if you have a look at those for reference. So finally, this is the like uh, crowning lecture for the course after a lot of difficulty actually getting it uploaded. Now it's gonna be this. This should work. Finally got my one of my other classes lectures uploaded after a lot of other difficulties. So this will do it for the course. So anyway, the last lecture where I ended with graph theory was I had done an example using the Fiedler method to partition a graph, and in that example we saw that it partitioned it in the way that we kind of expected it to. And so I thought I would do a couple more examples of the Fiedler method to give you an idea of what can go on. And I'm going to list out the properties that the examples that are worked in the online notes have, because they give you pretty much the full range of experience, what you can expect with these. So I'm not going to do like every single example that's done in the online notes because it would take too long, but you can have a look at those, and it's explained really well, and the pictures are really nice. So a lot of this actually just reading over the notes will do you a lot of good. Like I said, this is going to kind of serve as more of like a gloss or like a quick explainer for some of these things. So look with me on page 11 of chapter 13. So chapter 13, page 11, example. So this is example 13.3. So this is the first thing I want to look at. This is picking up exactly where we left off the last lecture. So example 13.3 says consider the following graph. So there's the graph drawn out there. If you write out its Laplacian matrix, there it is listed out below. You can refer to the previous video to remember what the Laplacian matrix is or how you find the Laplacian matrix. So the eigenvalues of the Laplacian matrix are listed in order there below. So 0 is the first one. The first non-zero eigenvalue listed in order like this is 0.4869. So remember, the Fiedler value is this smallest positive eigenvalue of the Laplacian matrix for your graph. So that's the Fiedler value. So the Fiedler value in this example is 0.4869. A Fiedler vector is an eigenvector corresponding to that value. So on the next page, at the top of page 12, is Fiedler vector. So there it is. So some of the entries, 0.38 minus 0.20, 0.50, 0.07, and so on. Okay. And so remember how this goes. So the Fiedler method uses the basic Fiedler method uses the signs of the entries in the Fiedler vector to tell you how the graph is supposed to be partitioned. And so note that so use sign of entries in Fiedler vector to determine partition. Again, I'm going to talk about some examples here just in a few minutes that shows when this is not necessarily the best thing to do. This isn't always guaranteed to give you the most balanced partition. I mentioned this last time. But this is like a pretty standard and certainly an easy way to go about doing it. So according to this, the positive sign, so entries 1, 3, 4, so 1, 3, 4, 6. So entries 1, 3, 4, and 6 are positive, and entries in this particular example, and the other entries, so entries 2, 5, 7, and 8 are negative. And so a suggested partition, so thus a reasonable partition is the partition where I group all the corresponding positive entries 1, 3, 4, and 6 together. So 1, 3, 4, and 6 are grouped together, and the other entries, the negative entries, are all grouped together. So 2, 5, 7, and 8. And there's a picture of this on page, picture on page 12. Okay, so page 12 in chapter 13, the notes, has a picture of what this amounts to. So notice that, so the labeling on you can look at the example to see the labeling on the graph. So, so 1, 3, 4, and 6 in this case would be on the left in this picture on page 12, and 2, 5, 7, and 8 are grouped together there on the right. And so essentially you have removed the 2, 4 edge and the 4, 7 edge. You've removed 2 edges there in order to form this partition. Okay. Now remember what it is that a partition was doing. So a partition was, like, what we were doing with the Fiedler method was we were trying to minimize the cut, right? So the cut was, we wanted to minimize the number of edges that were being removed while simultaneously keeping the size of these partition sets the same. So in this case, the size of the partition sets are exactly the same. There's 4 vertices in each of the subsets, right, that make up the partition. Okay, so so you can see that picture there. That worked out really nicely. Let's look at example 13.4. So example 13.4 on page 12. You can see, again, I'm not going to draw that out. So I have vertices 1, 2, 3, 4, 5, 6, 7 on the left, and vertices 8, 9, 10 on the right. Looks almost like some kind of fish or something. So if I draw out the Laplacian for that, it's a massively gigantic matrix. But there's the Laplacian matrix right there. It has some list of eigenvalues. So if I list those out in increasing order, it's the second value that's the Fiedler value. So smallest positive eigenvalue. So in that case, this is on page 13. This is 0.2357 is the Fiedler value for that example. It says, since this positive graph is connected, yep, that's one of the things you're guaranteed. Fiedler vector is an eigenvector corresponding to this. Using technology, using MATLAB, the Fiedler vector in question is listed there. So 0.11, 0.25, 0.33, 0.33, 0.25, 0.11. You see there's a lot of repeating entries here, and then 4 negative entries rounded out. And so using the Fiedler method would mean taking entries 1, 2, 3, 4, 5, and 6, taking them all together, and then taking the last 4 entries. So Fiedler method suggests a partition, in this case, first 6 taken together. So 1, 2, 3, 4, 5, 6. And the remaining taken together. So 7, 8, 9, 10. And you can see what that looks like. So the picture is at the bottom of page 13. So pick at bottom of page 13. And so looking at this, so if you look at how this has been done, if you just look at this graph with these two edges removed, you might say, wait, this is not what I would have done, right? So if you ask me to separate this graph, going back looking at the original graph at the bottom of page 12, if I'd asked you to separate this graph in some consistent way that minimized the cut, you would have definitely removed the 7/8 edge, right? That's almost certainly, you could ask a kid which of those to remove to separate in some nice way, and almost everybody would say remove that single 7/8 edge. But notice that if you did that, the set would be, the graph would be unbalanced, right? The two sets in question would be unbalanced because one of the partition sets would have, if you remove the 7/8 edge, one of the partition sets would only have 3 vertices, and the other would have 7. So that's like massively unbalanced. Whereas if you do this, yeah, you're removing an extra edge, but you have a subset containing 4 vertices and a subset containing 6. So that's more balanced, but they're not quite equal, right? So for this particular example, the cut of this P is 2 because it removes 2 edges, notice that we could actually do better. Even if we could find another partition with cut 2 that did a better job of actually splitting these in an equal way. So I will see what that would look like, but I'm just going to say right now, note we can do better, i.e. we can have cut of P equal to 2 while the size of the two partition subsets are equal. Here, note that if this is V1 and this is V2, the size of V1 is 6 and the size of V2 is 4. So they're not equal. The Fiedler method, of course, depending on the number of vertices, they're not always going to be able to be equal. The idea is that they should be as equal as possible. That was one of the goals of the Fiedler method, right? And so remember that, so recall, what is it that we originally wanted? Okay, so what is it that we originally wanted out of this? So the answer to that, the thing that we actually originally said that we wanted, so we wanted a partition P, and partition by definition was made up of 2 subsets, V1 and V2. So we wanted a partition such that cut P was minimized while keeping the size of V1 roughly the same as the size of V2. All right, this was really what the Fiedler method was doing for us. Okay, so the observation here, and this is covered on page 14 of the notes, is that you can formalize this by saying that if you have a partition of a graph G with n vertices, you can define this by choosing a vector x, and each vector in x is +1 or each entry in the vector x is either plus or minus 1. Having such a vector, you can then create a partition by taking the vertices I that have x sub I equal to +1 as one subset, and take the vertices I with x sub I equal to -1 as the other subset. And so that's what you get. It's a choice of vectors I, and then keeping those subsets equal amounts to having that sum be equal to 0. And keeping them almost equal means having that sum be almost 0. So to write this out, right, using the Fiedler method, our idea was our partition was the set of vertices if our x is our Fiedler vector, if you like, or not really our Fiedler vector, it's the sign of the Fiedler vector, so sign of Fiedler vector. So x is a vector in Rn, and each x sub I is plus or minus 1. Okay. And the way that the partition is formed is you take 1, it's the set of all I such that x sub I is equal to plus 1, and the other is the set of all I such that x sub I is equal to minus 1. Okay, so you can call this V1 if you like, and this V2, doesn't matter how we label them. Okay, so keeping the size of V1 equal to the size of V2, that implies that the sum of all the x sub i's over I is equal to 0. Right? Because if they have the exact same size, then there's going to be the same number of plus 1s as minus 1s, so summing them all together, you're going to get 0. Right? So then, continuing on, thus keeping the size of V1 approximately equal to the size of V2 implies keeping this sum of the entries in that sign vector approximately equal to 0. So not exactly equal to 0, but approximately equal to 0. All right, so this is really our goal of the Fiedler method. So there's a following lemma, and before the lemma is stated, there's a little caveat that in the sum you're not double counting. So if you have an edge, call it the ij edge. An ij edge is a ji edge. So so we only count an edge once in the sum that I'm going to write out. So there's a lemma. This is on page 15 or 14, I think, in the notes. So the lemma says for any partition P, so I can write that as V1, V2, of a graph G with edge set. Can't remember if I defined edge set before E. So the edge set is exactly what it sounds like. It's the set of all edges, but I'm not counting them twice. So for instance, maybe we'll do a little aside here. So if I have a graph that is, we'll say it's 3 vertices, 1, 2, 3, and let's see. Let's make it more interesting. Let's say 1, 2, 3, 4, and this is my graph. Okay, so my edge set E would be the set containing the 1, 2 edge, the 2, 3 edge, the 3, 4 edge, and the 2, 4 edge. Okay, so it is a set containing 4 edges, 1, 2, 3, 4. There they are. Note that the 1, 2 edge and the 2, 1 edge are considered the same thing, so there's no symmetry here. I would, if I wanted to be really technical, I'm a little bit off. If I wanted to be really technical here, right, I would, let's do some basic set theory stuff. I would have to say there's like an equivalence class where the edge 1, 2 is equivalent to the 2, 1 edge and stuff. I'm not going to get into any of that. I'm not going to get into any of that stuff. It's just, we'll just be, as intuitive as we want to be. The point is I don't want to double count edges, so there should be, the cardinality of the set should be 4. It should be the exact number of edges here. And so this is what my edge set is. So anyway, I have partition P of graph G with edge set E, and in this case I can actually just directly compute the cut in terms of the sum over this vector x in the and I'm summing over the edge set. So this cut is 1/4 the sum over edges, ij edges in the edge set E of this square of this difference, x sub I minus x sub j squared. So this might look a little confusing at first, and indeed we're actually not going to use this explicitly. We're more going to use what this tells us. Okay. In fact, I'm not even going to talk about why this is. It has a short proof. If you want to see it, it's at the bottom of 14. So what this means is that I should write out what this means. So if I want to minimize cut P, I need to minimize the 1/4 doesn't matter here. Minimizing the sum will do it. So I need to minimize the sum over the edge set E of x sub I minus x sub j squared. Okay, so I want to minimize that. Okay, and I want to minimize this relative to the condition that my sum from I equals 1 to n, so summing all the entries of this sign vector, is approximately 0. Okay, and of course each x sub I is plus or minus 1. It's one of those things. Okay, so this is what is meant by this theorem. This is our application of this lemma, I should say. So as the notes point out, this is actually computationally really intensive and would involve checking all possible combinations of the x sub I. So it gives an example. It says, for example, if the graph has 10 vertices, which is not that big of a graph. So if a graph has 10 vertices, and there are 2 to the 10, which is 1,024 possible x vectors. And if the graph has 100 vertices, then there are 2 to the 100, which is a pretty large number of possible x vectors. So this is not great, but we're going to loosen what we want a little bit. So this is where the next bit comes in. So the name of this section in the notes is what are we getting? So idea, we want to loosen this a little bit. So we want to loosen our requirements a little bit. Okay, and so to see what is meant by this, so there's old goal and new goal stated on page 15 of the notes. So the old goal is what I just wrote down. I want to choose a vector x that minimizes that sum with the conditions that the sum of the x sub i's is approximately 0 and the x sub i's are all plus or minus 1. So the new goal is to choose a vector x that minimizes that same sum with the conditions that they sum to exactly 0, so that keeps the size exactly the same. But the sum of the squares of the x sub i's is equal to n. Okay, and it says there that this is a slightly weaker version of the old goal. So new goal. So choose x to minimize the sum over the edge set of x sub I minus x sub j squared with condition that the sum from I equals 1 to n of the x sub I is actually identically equal to 0. So that's actually stronger. But the sum of the squares of the x sub i's is equal to n. Here's where the weakening comes in. Okay. So each of the x sub i's is actually not plus or minus 1. So the x sub i's are spread over the interval minus root n to root n. Okay. Okay. And they don't have any large gaps or disconnected vertices. So this is what is nicer. Now I'm going to read through a list. Okay, so this list is on page 15. So refer to page 15 for the conceptual bits that are nice here. So the question is asked, what will the x sub I values in this new x vector mean? So it says, consider the following observations. So the first condition makes sure that all the x sub I average to 0, meaning that they should be spread out around 0. The second condition prevents all the x sub i's from being too close to 0 and prevents any one x sub I from being larger than the square root of n. Okay, so minimizing the objective prevents any large gaps between clumps of the x sub I values. And so the reason for this is that the graph being connected guarantees that some vertex in the first clump must be connected to some vertex in the second clump. So a large gap between clumps would contribute to a large value, or would contribute a large value to the objective. And from the previous facts that I just listed out, you can see that it's not reasonable to have a few values less than 0 and many values greater than 0, because then they wouldn't average out to 0 unless there was a huge gap, and that can't exist. So you're not going to have any kind of clustering like that. If two vertices I and j are connected by an edge, then minimizing the objective means keeping the corresponding x sub I and x sub j close so that they only contribute a small value to the objective. And then lastly, if two vertices I and j are not connected by an edge, then the corresponding x sub I and x sub j can be further apart. And it says here at the end, the practical upshot of all this is that the x sub I are spread over the interval minus root n to root n, with no large gaps and no disconnected vertices having x sub I values which tend further apart, and with connected vertices having x sub I values which tend to be closer. And so what this means is that you can choose a place here to split the vertices into two groups, and that the vertices in each group will tend to be clustered together. So what this means, the main thing to get out of all of this, is that rather than just using as a binary thing the sign, right, whether it's positive or negative, you can actually choose a value here in order to split the vertices. You don't have to just use positive and negative. You can actually use some value chosen in this interval to split. So you could choose some value and say, take all the vertices larger than that value and split them into one set in the partition, and take all vertices smaller than that value and split them in the other set. So that value need not be 0 is the point, right? You don't have to choose 0. Choosing 0 would be picking just the sign, but you don't have to choose 0. You can choose some other thing, because in some of these examples that we're going to go over, sometimes 0 is not the best thing to pick to get a well-balanced minimizing partition. Okay, so it says, an obvious way to split is to take the vertices corresponding to positive values and those corresponding to negative values, and to put 0 in either one group or the other. But there are other choices, including splitting at the median. So that's an example. So more examples, and then we'll be done with this stuff. So more, and these are trickier examples. I'm not going to go through all of them exhaustively. Some of them have really, really big graphs. And it wouldn't be good for me to spend the time actually drawing them out or talking about them. So these examples have various properties. I believe these are listed in order. I might get the order. They might be slightly out of order, but so in the first example, there's a 0 in the Fiedler vector. So we've talked about how you can manage this. One is you just make a choice, right? You just make a choice and you decide to group it in one group or the other. Two, repeated values in the Fiedler vector might yield choices. So we saw an example, and we're actually going to revisit. We saw an example where you had a bunch of repeated entries. And so it might make sense to actually group those together in some way and kind of avoid double counting. So repeated values in the Fiedler vector might allow for better choices. So might allow for, we'll say, more judicious choosing. Okay. You could choose a K partition. Remember, a partition is a partition where K is equal to 2, so you could choose a K partition for K, say, strictly greater than 2. So you could actually split the graph into 3 pieces. That's something you could do. Fourth thing, you could have, so eigenspace corresponding to Fiedler vector is greater than, or has dimension greater than 1. Okay, and some other things. So some more different types of examples. So one, the Fiedler vector can give insight into the graph structure. Well, that's kind of our purpose of doing all this. Fiedler vector fails to be helpful at all. That's another possibility. So I'll do an example at the very end that shows when the Fiedler vector can not be that helpful. But first, let's do this bow tie example. So let's look at this example, which is 13.5. Again, so this is page 16. So 13.5, it looks like this. So I have this bow tie graph. So this is 1, has a label 1, 2, 3, 4, 5. Okay. All right, so then quickly, the Laplacian matrix for this is listed at the bottom of page 16. The eigenvalues you find in increasing order, 0, 1, 3, 3, 5. So the Fiedler value is 1, smallest positive eigenvalue. The associated Fiedler vector, so Fiedler vector is 0, minus 1/2, minus 1/2, 1/2, 1/2. Okay. That looks really small. Let me write it in decimals like it does in the book. So minus 0.5, minus 0.5, 0.5, and 0.5. There we go. Okay. So, all right, so here's my Fiedler vector. So, accordingly, then, just looking at the Fiedler vector, doing what I've been doing the whole time, if I split by sign, not caring about anything else, then I have 2 negatives. That's the second and third vertices, so 2 and 3. And then I have 2 positives, that's 4 and 5. But then the vertex 1 has a 0 in the Fiedler vector associated to it, which means I am free to choose. Well, just looking at this bow tie graph, you can tell there was going to be a problem with this one vertex since it is more connected than any other vertex in this graph, right? And so where it goes kind of splits things up in a bad way. You can see the choice totally determines what it looks like. So I would have 2 choices here. One, I could group vertex 1 with 2 and 3, the negatives, or I could group it with 3 and 4. So my 2 choices that make sense using the Fiedler method, one choice would be to group it with 2 and 3. And so leave 4 and 5 together. Or to group it with 4 and 5. And I can't really say which one is better, right? Because they actually have the same property. Okay, they have the same 2 properties. So, and what it says here, it says it's clear from both the graph and from the vector that the one vertex is more difficult to categorize than the others. So even though the Fiedler method doesn't explicitly tell us what to do with the vertex, the way the values are spread out, it makes the options fairly easy. So basically, you get these 2 choices. You can assign that 0 vertex to either group you want to. you can see this sort of behavior, that is the choices, even when the Fiedler method works and says more. So you can look at this fish example 13.4 revisited. So consider example 13.4 revisited. So so in this fish looking example, there's we already saw what the vector looks like. So you can note that a lot of the entries come in these pairs, and so that is done at the top of page 18. So at the top of page 18, there is a table listed, and this table says that vertex 9 has as its associated entry negative 0.49. Vertex 10 has the same entry associated to it, negative 0.49. Vertex 8 and 7 have two distinct entries for the vector. So vertex 1 and 6 both have 0.11 as their associated entries. 2 and 5 both have 0.25 as their associated entries, and vertices 3 and 4 both have 0.33 as their associated entries. So lots of repeated entries. Okay, so could we still do what we did in the first time we saw this example and just separate it by negative and positive? Yes, we could do that. And you saw exactly the partition that resulted when we did that. But another example is to consider splitting them in half and taking the smallest half and grouping them, and then taking the largest half and grouping those. And so how it was suggested here is, since 0.11 appears twice, you could split those two occurrences up and put vertex 1 with the first half and vertex 6 with the second half, or vice versa. You could do the opposite. And so when you do that, you get two different pictures. These are on page 18. So both these pictures are on page 18. You have a look at them. The first result is from grouping 1 with the later vertices, that is the smaller vertices, and the other is grouping 6 with the smaller ones. And you see the result there. So in fact, you get two partitions of exactly equal size. When you do this, that's still cut too. So that is kind of the important thing I wanted to notice. So note in both cases, cut P is equal to 2, but the size of V1 is equal to the size of V2. So they're perfectly balanced, and the cut is 2. Compare that with just doing it in like the direct method, splitting or partitioning by negative and positive, and we had cut of the partition was equal to 2, but the sizes were off, right? One had 6 and one had 4, I think. So this, using this modified Fiedler method, has given us a partition that's actually more balanced in some way, right? And you can continue on. So you could take both 1 and 6 with the first half, and the remaining with the other half. That would give you a size 6 and a size 4 again sets, and you can look at those. Those are on page 19. The two results of doing those differently. But if you are willing to have cut 3, well, then you can do other things too. So basically, these are things that you can toy around with to see essentially if it. You can basically use the Fiedler vector to analyze the graph to see what it is you want done. The idea is that you're accomplishing the same sort of thing. It's really just a question of whether or not you would prefer to study one piece of the graph in one way or another. The last example I was going to talk about before moving on to a general example of when things can go wrong is in 13.6. There's a more convoluted example of a pretty nasty graph. And MATLAB has been used to find the eigenvalues of the Laplacian matrix and look at its Fiedler vector. So this has all kinds of stuff going on. It's got repeated entries. It's got a 0 in the Fiedler vector. It's got all kinds of stuff going on, and so you basically have a lot of options here. And as it says, all these values are basically divided into 3 groupings. And so it might make sense to partition it into 3 subgraphs. And so that's essentially what's done. Instead of coming up with a 2 partition, it turns out that it might be more sensible to take that graph as it's drawn there and split it into 3 pieces in order to analyze it. And when you do that, you see on page 21, there's kind of a suggestion of how those 3 partitions should look, or what those 3 partition subsets, I should say, should look. And of course, in a graph, all that matters is vertices, edges, and how those are connected. So that you don't need to leave it looking so messy. You can clean it up, as they say. So cleaning those things up, you see what it looks like. So that's more or less it. If you look at the remaining examples in chapter 13, you can basically see the full range of what can possibly happen with these. At the end of chapter 13, there's a bit of MATLAB code that shows you how you can generate some pictures that actually look pretty nice and help you deal with these things. So that'll definitely help for your chapter 13 homework. Although, well, you don't need a lot for the chapter 13 homework that I assigned. And so one example of why the Fiedler method might have issues before moving on is, suppose that you have a graph that looks something like this. And so I have a graph so there's my vertices, here's my edges. Okay, so if I have a graph that looks something like this, one thing about the Fiedler method not being able to kind of pick out is the question of the closeness of vertices. So this is brought up at the very end of chapter 13. And the idea is, in a picture like this, you're able to say something like this vertex here and the vertex on the opposite side of this image, these 2 vertices are in some sense far apart. But the question is, how far apart is this vertex here that I'm pointing to and one of these that look like they're directly adjacent to it? So the thing is that you'd like to say that these are pretty close in some sense, but this is almost like a geometry. It's like a discrete version of a geometry problem with like antipodal points, or I should say conjugate points. So the Jacobi fields or something. So the idea here is you'd like to say that these 2 adjacent things are close in some way, and yeah, there's ways you could say that. You could just say they're adjacent. But the thing is that kind of intuitively, like, what if you went around the wrong way, right? Or what if they're not directly adjacent? So like, what about this one and this one? So yeah, you can get to it in 2 vertices, but what if you go around the long way? It apparently they don't look like they're that close. So this is one of the things that can come up. The Fiedler method actually has a hard time distinguishing from things like that going on. Anyway, so the remaining, the last 30% of chapter 13 is all of the theory for why the Fiedler vector stuff all works out. You don't need any of that stuff to actually understand how to use the Fiedler method to partition a graph, so I'm not gonna go over it. But you can read that if you're interested in it. But you definitely don't need it for any of the problems, either in the last final exam project or in any of the problem sets for chapter 13. So none of that's necessary. Anyway, so that's pretty much all I wanted to say about chapter 13. I probably spent a little bit more time on it than I wanted to, but that pretty exhaustively covers what you need to know. So anyway, now the very last bit, chapter 14. So chapter 14, you should also look at the notes while I'm discussing this, not because there's a lot of pictures or anything, because there's not, but because unfortunately there's a lot of long strings that it's nice to see actually written out, and it would take me a long time to write it if I wrote it all out, but it just helps with the exposition to be able to read it off and not have to literally copy everything down. Since in a classroom setting, right, this is Math 401 is meant to be a primarily group work and kind of a, you know, the way the exposition's supposed to be is more like a Socratic method, like Socratic dialogue type class. So teaching it online is kind of not ideal to how it's supposed to go, right? I'm supposed to be able to engage like groups of you are supposed to kind of have a discussion, but anyway, that's no sense crying too much about it. Anyway, so then the last thing that I wanted to mention for the semester, cryptography. The most important bits that you should get out of this, and essentially what you're responsible for if you haven't already taken a look at your homework or at the final exam problem that I assigned, is basically to understand the absolute basic. So I mean, this is a really, really basic method of encryption that's presented in chapter 14, but the reason for that is even though this method is basic enough that it wouldn't be used directly in exactly this form, it is good enough for you to understand how this works, and the application of what's done here is something that you can take and apply to a lot of basic cryptography. So like I said, so while this encryption algorithm we're going to talk about is not necessarily something that is going to be used by a lot of stuff, there is a lot of encryption that's done that uses something that is extremely similar to this, or is literally this, just very, very slightly modified. So anyway, we are going to be talking about like essentially a single method of encryption here. Like I said, obviously there's much more sophisticated methods of encryption that have advantages over this, but for the purposes of understanding what's going on, this will work just fine. And so the first thing that needs to be noted is mod 2 arithmetic. So if you haven't seen arithmetic modulo 2 before, all this is an equivalence relation that's put on the set of integers that says that two integers are the same if when you say divide their difference, right, by 2, well, you get one of two things, right? You have a remainder left over. You either get remainder 0 or you get remainder 1, right? So when you divide a number by 2, there's two possibilities. You get remainder 0, remainder 1. If you get remainder 0, that number's even, right? So that's called being congruent to 0 mod 2. And if you get remainder 1, then that number's odd. So that's called congruent to 1 mod 2. And so, for instance, 3 is congruent to 1 mod 2. All right. Congruent here we're going to use as an equivalence relation. So in fact, in the online notes, he might not even, he just says equal. That's perfectly fine. So we'll just say 3 is equal to 1 mod 2. Okay. Another example, so 2 is equal to 0 mod 2 because 2 is even. So 2 is even, so it's equal to 0 mod 2. 3 is odd, so it's equal to 1 mod 2. All right. 1 plus 1, which is equal to 2. Since 2 is 0 mod 2, 1 plus 1 is 0 mod 2. So yes, in mod 2 arithmetic, 1 plus 1 is equal to 0. Okay, it's still equal to 2, of course, but 2 is equal to 0 mod 2. All right, we can multiply. We could say 3 times 5, right? So here, I already wrote this 1 accidentally, so let's say 3 times 15. Right, so 3 times 15 is equal to, 3 times 15 is 45, that's odd, so this is 1 mod 2. Okay, so 3 times 15 is 1 mod 2. What about minus 1? Well, minus 1, you might say, wait, it's negative. Can I really say that it's odd? Well, the thing is that, one, yes, you can, but also you can think of adding 2 to it. Right? 2 is 0 mod 2. So if you add 2 to minus 1, what do you get? You get minus 1 plus 2, which is 1 mod 2. So again, how did I arrive at this conclusion? Well, minus 1 plus 2 is equal to 1. Right? But 2 is congruent to, or is equal to 0 mod 2. So 1 plus 2 is equal to 1 mod 2. Okay, that's the idea. All right. Okay. So, you can brush up on, you can practice your arithmetic mod 2 if you've never seen that before. It's pretty simple just because there's only 2 numbers that any given integer can be equal to mod 2, either 0 or 1, right? So given number is either odd or even, so that describes it, right? So if you're familiar with binary, right, that's essentially what you're thinking of here, right? You have 2 choices in each slot, 0 or 1. You can even use this for matrices. So the example they use is like if you have the matrix 1, 0, 1, 1 times 1, 1, 1, 1. So if you multiply through that matrix and go ahead and simplify to mod 2, this is, what would this normally be? So this is 1 times 1 plus 0 times 1, so that's 1 here. And then in this slot, this would be 1 times 0 times, so 1 times 1 plus 0 times 1, so that's also 1. Here, this would be 1 times 1 plus 1 times 1, that's 2, but that's 0 mod 2. And lastly, 1 times 1 plus 1 times 1, so that's 2, but that's 0 mod 2. Okay, so this even applies to matrices here. Okay. All right. So for most of this chapter, so he says he's going to use the notation for a vector like x semicolon b semicolon c for the vector ABC. So he says he's going to use this notation. I'm probably just going to write it as column vector when I'm doing this, but this is like MATLAB notation, right? So if you see this in the online notes, this is what's meant. And then the other thing that's mentioned is oftentimes, the vectors you're dealing with, you're thinking of the vectors, their entries are bits, either 0 or 1. And so, for instance, if you have a 5-entry vector, you're going to say, so like x, the vector x is in the set 0, 1 to the 5th. This means that x has 5 entries, each of which are either 0 or 1. Of course, you'll recognize this notation if you just think about it as like the direct product or Cartesian product of this set 0, 1 with itself 5 times or 4 times. Then this is the same thing. Anyway, okay. So what is our? This is just the background to set up what it is we're going to do. So then, how does the encryption actually work? So how encryption and decryption works. How our encryption and decryption works. So the idea is that you have some message, some data, right? Some info, right? And we're going to think about it as being some plain text. So we have plain text, okay, which we have listed. So this is at the bottom of page 4 in chapter 14. But say we have some plain text 101000011001111 and so on. So again, if you want to see the full thing, look at page 4, bottom. Okay, so page 4 at the bottom has a nice listing of what is going to be our plain text. So suppose Alice wishes to send the following binary stream to Bob without Eve intercepting it and understanding it. So this is the plain text, and this could go on indefinitely, all right? So there's a string of zeros and ones. Okay, so in order to encrypt this so that Eve may not understand it if she intercepts it, what Alice and Bob can do is the following. So first they create and share a key. So we create and share a key with those we wish to securely communicate with. Okay, so this key, of course, will allow the people that we want to be able to decrypt our message after we've encrypted it, right? So we have plain text we want to send. We encrypt it, right? We encrypt it, we send it. Then the person that we want to send it to has the key. They use that key to decrypt the message. And the idea is that if, and maybe I'll draw, a picture, right? So here's person that is nice. They have a halo over their head. And they take plain text, then they encrypt, and then they send that message to person over here, who's other nice person with halo. So here's Alice and here's Bob from the online notes. And so then decrypt the encrypted message using the key to get the plain text message that was wanted here. And the idea is that if there's someone in the middle, they have horns because they're mean. This is Eve. Okay, so if there's someone in the middle that intercepts the message at this point, well, it's already been encrypted. So the idea is that hopefully without the key, they can't decrypt it and understand it. So it's just an encrypted message. It just looks like garbage, right? There's nothing that can be gleaned from it. So that's the idea behind encryption, right? So the point is that if Alice and Bob create and share a key, so I'll get into what method they might use to do that and how they can go about actually sharing it. The idea is that the key is used to encrypt. Since the key is known by both Alice and Bob, it can then be used to decrypt later. So skipping Eve in the process, that's the idea. Now, there is a problem with this. So one, we're going to talk about methods of actually coming up with a key in the first place. The other thing is that the key has to be communicated in some way, right? So the idea is if my whole problem is trying to come up with secure communication method in the first place, then what method am I going to use to communicate the key? Right? So that's an issue. So then there's a couple of ways around this, right? So for instance, very similar methods to what I'm going to describe are used by things like Bluetooth protocols. I think is one of the examples. And in fact, how is the equivalent of the key in some form generated by Bluetooth, or how is it communicated between the device sending the Bluetooth and the device receiving it? Well, if you've ever dealt with Bluetooth, you know that there's a pairing mechanism, right, that involves you literally pairing the object with between receiver and the sender. And so this would be an example of a process that the generation of the key is responsible in crafting, right? So anyway, so that's just one basic example of something like this. Anyway, so what is the key going to be for us? So say our key consists of a string, so a binary string. Say the binary string, say 11010. Okay. All right. So we're not going to care right now about where this comes from or what this means, but that I'm going to say that that's our key. So then note, if we start with a 0 or 1 and add in mod 2 twice with the same value, this process cancels out. What do I mean by that? So 0 plus 0 is equal to 0 mod 2. Okay. Well, then 0 plus 0 is equal to 0 mod 2. And maybe you didn't see what I did there. So let's say 0 plus 1 is equal to 1 mod 2. But then, so I started with 0, added 1 to it, got 1 mod 2. Now I want to take this 1 and add 1 to it. So then 1 plus 1, well, that's 0 mod 2. So I started with 0 mod 2, added 1 to it, got 1 mod 2. Took that 1 mod 2 and added 1 to it and got 0 mod 2. So I started with 0 mod 2 and I ended with 0 mod 2. Right? And 1 plus 0 gives me 1 mod 2. But then now I have 1 mod 2 and I'm adding 0 to it, which is still 1 mod 2. So I started with 1 mod 2 and I ended with 1 mod 2. And lastly, starting with 1 mod 2 and adding 1 to it, I get 0 mod 2, and then I add 1 to it and I get 1 mod 2. So whatever I start with is what I end with if I add the same number mod 2 twice in succession. Okay. So this is why this is going to work as a key. So what does that mean? So idea: to use the key to encrypt the plain text. Well, I can just add the key to the plain text entry by entry. Then to decrypt, I just add it again. Now, you might say that, first of all, you notice an immediate problem. My key, let's go back here for a second. My key is only 5 digits long, right? So my key is 5 bits long, but the plain text in question was like really long. It was like, indefinitely long. Could be like 500 characters here, right? 500 bits of plain text. So the question is, how do I deal with that, right? So how do I deal with the fact if I'm going to add them entry by entry, then I need my key to be as long as my plain text. So what do I do? What I do is I just repeat the key. So after 5 digits, it just repeats. So in order to make in order to allow the addition, I repeat my key as many times as needed. That length of my key is, or I should say, the number of bits before my key starts repeating. The minimum number of bits before my key starts repeating is called the period. So the smallest number of bits before my key repeats is called the period. Okay. Okay. And so in this case, we have a key with period 5. So have a look so that I don't have to write like 30 characters here. So look at page 5 of chapter 14 to see what's going on. Okay, so what happens here? So Alice takes her binary stream and does addition bit by bit with the key mod 2. When she runs out of key, she just repeats the key from the beginning. So in this way, we think of the key as infinitely long and having period 5. We'll use the term key to refer both to the repeated fragment and to the infinitely long repetition. So then she sends the bits one by one. Okay, and so what's the idea here? I have plain text. So that's just my ones and zeros that I'm wanting to send. That's what I want my final message to be. So then I add the key to the plain text. I send them up, or I line them up. And I do the addition bit by bit. So then the ciphertext, the encrypted message, is just going along here on page 5. So 1 plus 1 is 0 mod 2. Then I do 0 plus 1, that's 1. 1 plus 0, that's 1. 0 plus 1 is 1. 0 plus 0 is 0, and so on. Right? I'm just doing mod 2 addition in every single slot. Okay, and that leads to my ciphertext. Note that my ciphertext is different than the plain text. Okay, that's kind of the whole point. So she then sends this final string, the ciphertext, to Bob, who decrypts it by doing another addition with the same key. So Bob knows the key, and to undo what addition with the key did, he just adds the key again. So he just takes the ciphertext, he adds the key to it bit by bit, and note that he recovers the plain text exactly as we expected. So then if Eve in the middle intercepts the ciphertext without knowing the key, she just has like a garbled block of this ciphertext, and she has no idea what it means. Right? And so if both of Alice and Bob have a key at their disposal, then this process is really easy to go about doing. Right. So it's actually like really fast to do this, and you're just adding here. It's very easy to code this, as the notes say. This is doing mod 2 is essentially like doing XOR, or exclusive OR. So you can easily do this. Is amenable to computation in an extremely straightforward way. And so then what is something that can help us make this process a little better? So one, as is said on page 6, the major issue with this is that the key needs to be created and shared between Alice and Bob before any communication can take place. Right. So it actually mentions here 2 Bluetooth devices. You can type a code given by one machine to the other machine. You're basically sharing a key in that way. And so in both of the cases that it uses, so one is the example of phone, where the key is hard-coded like onto the chip. Same thing with the cable box, or with the Bluetooth devices, as I said, shared by typing a code. So in all those cases that were mentioned, a problem is that the key with a larger period is more secure. Right. So keys with smaller periods can be brute force guess. We'll get into what it means to brute force decrypt something. For example, there are only 32 possible keys of period 5. So that's Something I didn't mention, going back here for a second, if my key is length 5, because we're using mod 2 and the only choices for our digits here are zeros or ones, I could have asked what's the total number of keys of length 5, and since I have 5 slots, they're independent, I can have repetitions all I want to, and my only choices are 0 and 1. That's a quick counting problem. I have 2 choices in each slot. There's 5 slots, so 2 times 2 times 2 times 2 times 2, right? 2 to the 5th. So 2 to the 5th, or 32, is the total number of possible keys of length 5. That is pretty easy to guess, right? You could literally set that up in MATLAB, no problem, and you could guess that key in no time, since there's only 32 possible keys. So the idea is you want your period to be longer and longer and longer, or larger and larger and larger, to prevent the sort of making brute force really, really easy. But the problem, you can't just say, oh yeah, I want a key with period like 5,000 or something, because the larger the period of the key is, the more memory it takes to store. If it's the hard-coded case, or if it's the time where you're transferring it, like in Bluetooth, then it would take longer to actually manually transfer the key, because it would be larger. So then the idea is it possible to create a key with a longer period using less data than the period? And the answer is yes, right? So the basic question he asks is it possible? Could you use 6 bits of data to create a key with a period of more than 6? And the answer is yes, using recursion. So you can define a key recursively to save on storage, to save on memory. So we can define a key recursively. So example 14.2, maybe I'll write it on this. I still have some room here. So example 14.2 shows generating, so what this example shows is generating a key recursively. To save memory. Okay, so then how to actually do this? So just quickly in this example, so let's say we could assign a key, which we'll say is a string x sub 1, x sub 2, x sub 3, okay, and so on with each x sub I in the set 0, 1. So it's every x sub I is either 0 or 1. So we could say let x sub 1 be 0, x sub 2 be 1, x sub 3 be 1, and we could define x sub n to be, say, x sub n minus 3 plus x sub n minus 2, or sorry, x sub n minus 1 mod 2 for n greater than or equal to 4. So we have defined a recursion that generates x sub n in this string from the term that came 3 entries before it and 1 entry before it, right? Okay. All right, and so if you actually see what this generates, so I mean, I can write this out quickly. So x sub 1 is 0, x sub 2 is 1, x sub 3 is 1. So then x sub 4, using this recursion, would be x sub 1 plus x sub 3. This is x sub 1 plus x sub 3, so this is 0 plus 1, so that's 1 mod 2. And then x sub 5 would be x sub 2 plus x sub 4. So x sub 2 is 1, x sub 4 is 1, so that's 1 plus 1, which is 0 mod 2. All right, and x sub 6 would be x sub 3 plus x sub 5. So x sub 3 is 1, x sub 5 is 0, so that's 1 plus 0, which is 1, mod 2. So if you wrote out what this string would be, it would be what, 0, 1, 1, 1, 0, 1, and so on. Okay. All right. And it turns out that this starts repeating after 7 bits. So starts repeating after 7 bits, or 7 entries here. And so the key in question is 0111010 is the key, and it has period 7. So period is 7, but how many bits did we actually use here? So we started with 3 initial values here, and then we started with 3 initial values, which were the coefficients in this recursion. So what do I mean by that? So I started out with 3 initial values, x, which was 0, 1, 1. Okay, written like this. And the coefficients on my recursion are the following. So my recursion is going to be x sub n is equal to, say, c, we'll call it c sub 1 x sub n minus 1 plus c sub 2 x sub n minus 2 plus c sub 3 x sub n minus 3. And so I have a vector c that is exactly those entries. In this case, though, that vector is, so the entry on x sub n minus 3 is 1, the entry, or the coefficient on x sub n minus 1 is 1, and the coefficient on x sub n minus 2, since it doesn't show up, is 0. So in this case, that c is 1, 0, 1. And so, using only, I had 3 digits stored here, 3 here, so using only 6 bits, I created a key of period 7. So period is greater than the bits. That's an example of how using recursion in this way can save memory. Okay. All right. And so, what this means, using, here we go. So I'm going to write down definition. So definition, a linearly recursive, or a linearly recursively defined key of length I. So that's the term being defined. Can be defined by 2 vectors. So the 2 vectors in question are S, which is what I called C up here. S is, no, C is right. It's what I called X up here. So S is the vector x sub 1, x sub n. It's my vector. And C is my vector c sub 1 to, oh, sorry, it shouldn't be x sub 1 to x sub n. It should be x sub 1 to x sub I. Okay. And this is c sub 1 to c sub I. Both of these are in 0, 1 to the I. So they are comprised entirely of zeros and ones, and there's I entries in each of them. So the key starts with the bits x sub 1 to x sub I, and for n greater than or equal to I plus 1, x sub n can be determined recursively by c sub 1 x to the n minus 1 plus c sub 2 x to the n minus 2 all the way up to c sub I x to the n minus I. And this addition is done mod 2. Okay. This might look a little bit more complicated than it actually is. Okay. All right. Notice I made no mention of period here because the length of this recursively defined thing is just telling me how many bits I have in this initial string. The idea is that this is going to generate some string, and its period, of course, could be bigger than I. I mean, in fact, that's kind of the point. That's exactly what I want to happen. Okay, so that's what that means. We call K, which is the vector S taken with the vector C, to be the generating pair. So, oh, I'm off camera. So we call the vectors S and C to be the generating pair for our key. Okay. So theorem, such a key is reversible. Meaning, if we know any I bits, we can find all previous bits. Okay, so any I bits you know in the key, you can recover any part of the key you want from those. Here's a quick definition. So the period of the key is the shortest number of bits after which the key repeats. So shortest number of bits after which the key repeats. Okay. And lastly, a linear recursively defined key of length I has period less than or equal to 2 to the I minus 1. Okay, so there is some relationship here, you might have guessed, but this is what it is. All right. So there's a couple of examples here in the online notes that actually shows you the generating pair and how good this is. So, for instance, in the example we just looked at, the generating pair has length 3 and generates a key with period 7, which is 2 to the 3 minus 1. So that's like as good as you can get. But a couple more, so he does a couple more examples of a generating pair that has length 5 and generates a key with period 31. And so if it's length 5, then the biggest its period could possibly be would be 2 to the 5th minus 1, which is 31. So that's as good as you can get. Okay, so with as few bits as possible, you've generated a key with period as big as possible, right? So obviously here, since you want the period to be as big as possible, and the biggest it can be recursively defined like this is 2 to the I minus 1, this is just showing you that those cases were sharp. Both of them were. Okay, and so this brings us to, so why did I go through all this process of showing like the process of generating the key and how like this notion of frequently you would have the key recursively defined in order to save on memory, because kind of the point of this chapter is not so much the encryption bit, it's how to decrypt, right? How to break the encryption. So, big question is, how do I break the encryption? So there's going to be two methods. These are covered in your homework. So answer. The methods that we'll talk about are brute force plus refined brute force. Now, as it turns out, if you're interested in forces, just force, if you're actually interested in questions like this, sadly, most encryption that's used for important stuff is essentially impossible to break by brute force like this. So knowing absolutely nothing, doing brute force is pretty much impossible. You can't really hack like that. In fact, if you really want to hack, right? Like what do you do? Well, what you do is you email somebody and you're like, oh, I'm like a warlord from Antarctica, and I have raided the ancient civilizations of the penguins of Antarctica, and I have acquired a massive hoard of gold, Antarctic frozen gold, and I can't access it right now. Right? I've been locked out of my vault, but I could get in my vault if you emailed me all your passwords. And if you do that, then I'll give you a share of my Antarctic gold. Right? That is essentially how hacking goes. That's basically the current state of the art when it comes to effectively hacking someone. So and I'm not lying. If you want to, like I said, I'm only slightly being facetious here. The point is when it comes to breaking encryption, practically most of the encryptions used is just too hard to break, and typically what is done instead is social engineering stuff. So literally getting people to send you their passwords if they're that stupid, or taking advantage of, you set up a fake site and have people, oh, you need to go to this site and change your password, right? And it's some site that you're logging all their keys, right? Or if you want to even go better, right? Like installing a keylogger on someone's computer if you have access to it. Things like this. Right, these are what is done, and I'm actually going to get into that a little bit, just not like specifically, but what I'm saying is when it comes to some of these methods, you might say how would I come across some of this info that's going to be required? So we're going to talk about brute force and refined brute force, and some of the info that you might come across would come across from snooping, literally from snooping, from eavesdropping, from maybe you have limited access to a computer you're not supposed to, right? Something like that, right? This is where all this stuff factors in. Anyway, so the idea is suppose that we basically have a part of the key, and we want to come up with how it's generated, right? So what this is described as on page 8 of your notes is, one option could be a brute force approach, since the recursion relation has each bit being a linear combination of some number of previous bits. We can take a portion of the key and take a trial and error approach. What this means is we first check if a linearly recursively defined key of length 2 works. If not, we check if one of length 3 works, and then if one of length 4 works, and so on. Right? So idea So this is the brute force method, not refined brute force, just brute force. So brute force method is we have part of key, and we wish to come up with the recursive generation or generators of the full key, right? All right. So the reason why this is just brute force is we are literally just going to do purely trial and error. So purely trial and error. What do I mean? So let's look at this example 14.5. So what does example 14.5 say? So suppose we obtain the following portion of the key. So suppose the key we have is 0, 1, 1, 0, 1, 0, 1, 1, 1. Let's see, did I get all that? 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. There's 4 of those. Okay, 0, 0, 0. 1, 0, 0. Okay, so that's the portion of the key that we have. So then the way that this goes is you proceed by asking progressively as follows. So question, could a linearly recursively defined key of length 2 work? So question, could recursively defined key of length, so this is linearly recursively defined key of length 2 work? Well, what does it mean for one to work? Right? If that's the case, then x sub 1 is equal to 0, x sub 2 is equal to 1. That's just from looking at the key. And x sub n is equal to c sub 1, x sub n minus... oh, they're labeling it backwards, whatever. So I think in the previous or a couple of pages ago, I had labeled it counting up instead of counting down. That's fine. I'm just gonna write it as the example has. It doesn't matter. So c sub 1 x sub n minus 2 plus c sub 2 x sub n minus 1, and that is for n greater than or equal to 3. And if this addition is done mod 2. Of course, and so what this means is that, so applying this to x3 and x sub 4, you would get, so x sub 3 would be equal to c sub 1, x sub 1 plus c sub 2, x sub 2, and that's mod 2. And x sub 4 would be equal to c sub 1 x sub 2 plus c sub 2 x sub 3. Again, mod 2. Okay. Which, if we actually just plugged in what these things were, what would I get here? Meaning plugging in from the key itself what this would have to be. So this would be 1 is equal to c sub 1 times 0 plus c sub 2 times x sub 2 is 1, mod 2. And x sub 4 is 0. So 0 would be equal to c sub 1 times 1 plus c sub 2 times 1, mod 2. Okay, which I can write as a matrix equation. So as a matrix equation, this is 0, 1, 1, 1 times C1, C2, and that is equal to 1, 0 mod 2. And so this is mod 2. So that's a matrix equation I get. So this matrix equation has a solution. This has a solution. The solution is C sub 1 is equal to 1 and C sub 2 is equal to 1. So we guess, coming back here to our original guess on what this recursion is, so we guess that x sub n is equal to x sub n minus 2 plus x sub n minus 1. Okay. All right. And then you test it on the fragment of the key that you're given. But you'll note that it fails at the 6th place. So x sub 6 is bad. So note x sub 6 is not equal to x sub 4 plus x sub 5 mod 2. Okay. So it didn't work. Now, well, this is called brute force for a reason, right? So now what do I do? Question. I ask myself, could a linearly recursively defined key of length 3 work? Could a linearly recursively defined key of length 3 work? So, proceeding as before, we get a matrix equation. The matrix equation we get is 0, 1, 1, 1, 1, 0, 1, 0, 1 times C1, C2, C3, and this is equal to 0, 1, 0 mod 2. It turns out this has no solution. There's a couple ways you could see this. One, the columns sum to 0 mod 2, but this column doesn't, so this can't be a linear combination of those columns. That's one way of seeing it. Okay, so length 2 or 3 can't work. So next question. Could a linearly recursively defined key of length 4 work? Okay. So we get the matrix equation. The matrix equation we get is 4 by 4 this time. So 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, and 0, 1, 0, 1. That's the matrix times C1 through C4. And that is equal to 1, 1, 0, 1 mod 2. Okay. And it turns out this has a solution and everything matches up. Okay, so this has solution. Its solution is C sub 1, which is 1, C sub 2, which is 1, C sub 3, which is 0, and C sub 4, which is 0. And so the recursion that you get is x sub n, which is x sub n minus 4 plus x sub n minus 3. And this is for n greater than or equal to 5. And this works. This generates everything that is visible to you. Okay. All right. So a couple of notes. The matrix equation that you get is actually pretty deterministic. So note the matrix equation. This is important for doing these problems. So the matrix equation we get isn't so bad. And how did we know that it worked? We checked it against the key that we were given, right? So that's the point. So the matrix equation we get isn't so bad. So for length m, that is, we're testing a key of length m, we get the following. So the matrix in question is x sub 1, x sub 2 through x sub m are my entries in the first row. And then we just shift x sub 2, x sub 3, all the way to x sub m plus 1. And going down this way, this is x sub 1, x sub 2, all the way to x sub m. This is x sub 2, x sub 3, all the way to x sub m plus 1. And you see how this pattern is working out. We go all the way to x sub 2m minus 1. So this is my matrix. Since it's length m, coefficients c that I'm looking for go up to c sub m. So this is an m by m system. And then the vector I get here is x sub m plus 1 up to x sub 2m. And this is mod 2. Okay. So this is the equation we get. Once you understand this, now it's a lot easier to set up the brute force chosen. It says, notice the first column is the m bits of the key starting at x sub 1. Second column is the m bits of the key starting at x sub 2, and so on. And it notes that this is computationally intensive. That shouldn't be surprising, since it is literally the brute force method. So brute force method is kind of nasty, but once you have this, at least you have reduced it to just a few matrix equations you're trying to solve for. And once you solve, you check to make sure that that solution actually matches up with the fragment of the key that you have, and that's it. That's how you do it. And then the refining brute force. So note refined brute force, which is the last thing we'll mention on guessing the key or on brute forcing the key. There is a theorem. So luckily for us, there is a theorem that makes things much easier. Okay, so I need room for this theorem. Okay, so here's the following theorem. So for any given m, I can define my matrix big M to be the matrix I wrote before. So x sub 1, x sub 2, all the way down to x sub m, and this goes over in the same fashion, all the way down to x sub 2m minus 1. Okay, then a couple of facts. So one, if the determinant of this matrix that you've written down is 1 mod 2, then no linear recursion of length less than m will satisfy the sequence x sub 1, x sub 2, all the way up to x sub 2 m minus 1. And secondly, if the determinant of this thing is 0 mod 2, this is the only other possibility. And if there is a linear recursion of length m which does satisfy the sequence above, then there is a linear recursion of length less than m which also satisfies the sequence. Okay. All right, so I'm not going to go through the proof of it, but what does it say that is the most important? So what this means, star fact, the length of the shortest linear recursion relation will be the largest m for which the determinant is equal to 1. So the length of the shortest linear recursion relation will be the largest m for which the determinant of that matrix, big M, is equal to 1 mod 2. This is the most important bit. Okay. Once you know that and can quickly check these determinants, then this method of using it before is this method of going through the example in the brute force way is exactly how you find the linear recursion relation. So the refined brute force allows you to quickly figure this out. It means that this checking and all these questions you ask, you don't have to do it step by step. You can actually just quickly compute these determinants and toss out everything else. Okay, so then once you can obtain such an M, the solution is just by solving that corresponding matrix equation mod 2, and that's it. So the list of the refined brute force method is at the bottom of page 12 and the top of page 13. It's like the full list of the refined brute force method. There's an example that's done right after that tells you how to do it. You're given a key fragment consisting of 50 bits, and it shows you exactly how to do it by very quickly computing those determinants, generating those matrices. There's a bit of block. There's like a block of MATLAB code at the end of this chapter 2. It's kind of helpful, so you should have a look at that. But anyway, that does it. So so this gives you everything you need in order to solve all the problems that have been asked, from you from chapter 14. So that does it. So I think I'm going to end the lecture here, and I will see you all during the problem session. So problem session is going to be on Wednesday during class time. So Wednesday starting at 3:30, I think is when I said. It was at the time of our original final, so I believe Wednesday starting at like 10:30 or whatever is when I said. So that's going to be when our discussion or our problem session is going to be. So I will see you all then.